All right, hi everyone. Welcome to the little video recording for today's lesson. Hope you had a great weekend. Hope logs have been going well for you. We've been evaluating logs so far, and I hope that's going well. Today we're going to pivot slightly to approximating logs. Right. So logs don't always have nice outputs. It's not the case that every output of a log is an integer or some nice fraction, a rational number. You could have an irrational output to a log. And while it may be a little hard to approximate that to many decimal places, you definitely can approximate to a fair degree of accuracy. And so today we're going to talk about how to approximate logs without a calculator. All right. For that, we're going to need just sort of a random number. So if you have a random number, go ahead and shout it out. 539. Cool. 539. If you said 539, I bet you're just going crazy. You're just going nuts right now. You're like, oh my God, I don't know. But if you guessed 538, you'd be like, oh, stings. So close. Anyway, let's talk about I'm sorry, not equal. Let's talk about how to approximate the common log of 539, right? In fact, I'm actually not even going to really think about the log for a moment. I guess I kind of will. It's important to know that the base is 10 here. Right? If I write this as a common log, then we're going to be dealing with base 10, right? But 539, if I think about the powers of 10, is going to be greater than 10 for sure. But I want to get a little closer. I want the sort of the closest power of 10 that would be less than 539. And so I think that would be 100. Right? 100 is the power of 10, definitely less than 539. Another power of 10, past 100 would be 1000. 1000 is greater than 539. And there really aren't any other powers of 10 that are, closer to 539 than 100 and 1000. So we kind of have sort of this compound inequality, right? 100 is less than 539 is less than 1000, right? But we can take, the log of each of these components of our inequality, right? Of each part of our inequality. And so if I rewrite that more nicely, then we would find that the common log of 100 is less than the common log of 539, which is less than the common log of 1000. Right? And that's true because the, real numbers are always increasing just sort of as you move through the real numbers, and a logarithm's output are also always increasing as you increase the input of the logarithm. Right? So this inequality is going to hold when we take the log of all those quantities. Right? So now we're at common log of 100 is less than the common log of 539 is less than the common log of 1000. But we know the quantities, right, on the left and right of that inequality. The common log of 100 is 2, right? 100 is 10 to the second. So the output of log base 10 of 100 is 2, right? And the common log of 1000 is 3, right? 10 to the third is 1000. And so we don't know exactly what log of 539 is, right? But we definitely can certainly say that we feel confident that log of 539 is between 2 and 3, right? So for a lot of applications, such as graphing in particular, right, that may be enough. You just want to know sort of what two integers am I going to put my, output for the log of 539 between, right? Between, y equals 2 and y equals 3. Cool. I can sort of find a point that way. I think for a lot of cases, this may be enough. We want to go a little bit further, right? In terms of, let's say you wanted maybe one decimal point of that approximation, or maybe even two, right? It's 2 point something, but what's that something that comes after? It may be worthwhile to sort of think about sort of the difference between 100 and 1000 and sort of where 539 falls in that difference, right? So for, a metaphor here, I'll throw down a number line, right? Let's say that this is 100 and this is 1000, right? 539 sort of probably kind of in the half of that, in the middle of that, and say 539 here. There's a difference of 900 between 100 and 1000. And from 100 to 539, 439, right, units sort of gets us to 439 900ths of the way from 1 to 1000. I think I said that grammatically correct. Hope I did. So 2 and 439 over 900, right? If I'm thinking linearly, is sort of the way that I might approximate that. And if you're sort of a little good with fractions, you may know that that's, approximately 2.44-ish. I'm actually, that's a little low. So, that sort of even gets you in the ballpark. I would say the margin of error on that right now, I would say plus or minus 0.3. Actually, no, I'm going to take away the minus because this method of estimation for logarithms in particular is actually always going to underestimate. So really, I would actually go so far as to say, I'm going to say 2.7. I'm doing this without a calculator. I don't have a calculator in front of me. I'm about to actually check in Desmos though. 2.7, let's say 2. And this is where I'm going to hit the plus or minus. Plus or minus 0.05. I'm really flying blind here. Okay, I'm going to check this in Desmos. And some of you, as I'm doing this, are going to be like, I don't believe that he actually did that. I think, because that 539 wasn't random. I think he had it prepared. And to that I say, some of your haters. I just threw that in Desmos. It was 2.73. Yes, let's go. All right. Estimation technique remains undefeated. All right. You can check that in Desmos if you want. So apparently, according to Desmos, the log of 539 is approximately 2.73. What up? Let's go. Okay. That's basically the approximation technique. The main part that I want you to get out of that is that if you just think about the consecutive powers of whatever your base is, right? So for this, we did base 10. So I'm thinking about consecutive powers of 10, right? Where does 539 fall? Sort of in that number line with my powers of 10. And then you can sort of use your logarithms to sort of narrow in between two consecutive integers that you want to approximate with, right? So for example, if this was log base 2, right, then I'm thinking maybe, okay, between 4 and 8, or between 8 and 16, right, or between 16 and 32. You're thinking about consecutive powers of your base, and that sort of gets you to narrow in on the range of possible outcomes for your log. So there you go. You can use that to work through that last page of the notes, right? So you have a lot of logarithms there, and I'm just asking you to sort of either find exact values of those outputs, right, or approximate what the logs might be. And then you're going to put those in ascending order, right, from least to greatest. I'm actually going to give you the answer right now, just so you have it. And that's a way for you to check your work, but I'm not actually going to tell you what the logs are. So that's going to be part of it. You got to figure out what the logs are to see whether you are approximating or evaluating these logs correctly. All right, so here comes the answer. If you put these in the correct order, the logs that I gave you, this would be A is less than, C is less than, B is less than H, D, G, F. I didn't give myself enough room. That's rough. K, and then J. All right. So just go ahead and try to finish off that last page, right? Make sure that you check your answers. You can work with your teammates and make sure that you follow all of the directions in Canvas because you got to submit certain things, certain places, and there's more stuff to what you're doing today. All right. But I hope today goes well. See you tomorrow. Adios.